when the output is continuous. For instance, the AWGN channel.
Can I ask one question about yesterday?
Yeah.
When you said we used channel 3 times in that exercise you said we used channel 3 times. It means, okay, a 0 comes, encoder make it 3 zeros,
Yeah.
and channel transmit each 0 at each time.
One at a time.
One 0 at a time, or 3 0
yeah.
at a time.
1 0, then the second bit, then the third bit. We are using the channel 3 times. Okay, we calculate the capacity of a channel, supposing that we are using the channel just once. But in practice, we will use our channel 1 million times, 1 billion times, and so on. We transmit a long sequence of bits. Okay. So when we use a code, and we say the block length of the code word is capital N, supposing that the channel is binary, we use the channel n times to transmit the first bit, the second one, the third one, and so on. And then we start again with another block, the information and another code word. Okay, so we want to study the behavior of channels with a continuous output, for instance, and maybe even a continuous input. For instance, a very common channel is the AWGN channel, where, for simplicity, we can transmit, for instance, two levels, +1 and -1. And what we receive is what we transmitted plus some noise, for instance, a Gaussian sample of noise. So we want to extend the concept of mutual information and capacity to channels with continuous inputs, maybe, and continuous outputs. Okay, and suppose we have a channel where the input is discrete and the output is continuous. Do we really need extending our concept of mutual information to this kind of channel? Well, we could say the mutual information between x and y can be evaluated, can be defined this way, also when the output is continuous. H of x minus h of x given y, which means the expected value of the logarithm of p of x given y divided by p of x. And this could be a good definition because x is discrete, the alphabet is discrete at the input, and so we can talk about probabilities of the input and probabilities of the input given the output. Okay. Of course, when we evaluate such an average, we have a summation with respect to x and an integral with respect to y, since y is a continuous random variable. Anyway, no problem. We can define the mutual information this way, and then we can look for the maximum of the mutual information with respect to the input distribution and say, okay, this is the channel capacity. No problem. We know that in general we could write the mutual information also this way: h of y minus h of y given x. Okay? But in this case we are in trouble because y is a continuous random variable. So what is the entropy of a continuous random variable? And what is a conditional entropy, conditional on x, again of a continuous random variable. In a sense, we could say, okay, no problem. We will not use this expression of the mutual information. We will use only this one, and the problem disappears. But suppose that also the input is continuous. The input is continuous, and the output of the channel is continuous. And now, even this equation for the mutual information does not work unless we are able to define the entropy of a continuous random variable. So, better to be able to introduce a definition of entropy of a continuous random variable. Okay, let's look, for instance, at y and the probability density of y. Suppose it is something like this. Okay, what is the entropy of a continuous random variable? Our random variable can take any value in this interval. For instance, maybe y is equal to 3.5321729 and so on, because in theory we are assuming that y is a real variable. So maybe we have an extremely long, an infinitely long sequence of digits. Okay. This is what we do when we say, okay, this is a continuous variable, a real number. Okay, how many digits do we have? An infinite number of digits. So, if we try to represent this number as a block of binary digits, that is, if we turn from the decimal representation to the binary representation, we need an infinite number of bits. So we should say that the entropy of a continuous random variable is infinite, because we really need, we would need an infinite number of bits to represent the value of the real variable exactly. Okay? So h of y should be infinite. Not too useful, because probably we will discover that also h of y given x is infinite. And so infinite minus infinite, we don't know. Well, maybe h of y does not exist, it is infinite. Maybe h of y given x is infinite as well. Maybe the difference is finite. And we are looking for the difference because we want to evaluate the mutual information. We don't care about the entropy. Okay, it is infinite, no problem, because we need an infinite number of bits. We don't care about it. What we really wanted to find is a way like this one to evaluate the mutual information. Okay. Suppose you divide the interval here in small sub-intervals whose size is capital delta. Okay. You can say, okay, let us try to approximate the entropy this way, as a summation of P of y sub I times delta. This is the probability of being in a small interval of length delta, multiplied by the logarithm of 1 divided the probability. Okay? And then one could say, let's take the limit when delta goes to 0, and let's say this is the entropy of a continuous random variable. And we see a problem. No problem here, of course, because this is what we need to turn this summation into an integral. A small piece of probability, the probability density times the interval length. Okay, no problem here. The problem is here, the logarithm of delta. And the logarithm of delta goes to infinity if delta goes to 0. So when we try to shrink the intervals, the entropy increases and goes toward the infinity, as we expected. Okay, something like this will happen also when we evaluate the entropy of y conditional on x. Exactly the same problem, because even conditional on x, y is a continuous random variable. So we have this term, actually minus the logarithm of delta, because here delta is at the denominator. We have this term also in h of y given x. But then you see that the two terms cancel. Okay. Let me show this another way. Let's try to modify this equation. Let us multiply the numerator and the denominator by the probability density of y. Note capital P here, probability, a lowercase p here, probability density. Okay? And now, P of x given y. And now, let's divide by P of x, and we obtain the expected value of the logarithm of P of y given x divided by, lowercase b divided by P of y. Okay? And let us expand this. This is this term, for instance. It is an integral of P of y times the logarithm of 1 divided by P of y okay, this is the expected value of the logarithm of the denominator. Okay, and this is minus P of y times the logarithm of 1 divided by P of y given x. Actually, okay. This is the entropy of y. Okay, we have also a summation with respect to x here. So you see, no delta here. In a sense, we have a probability density here multiplied by some small interval delta. A probability density here multiplied by the same interval delta. So probabilities here and probabilities here. But you see that there is a cancellation of capital delta. And so, finally, we could say, okay, instead of saying that the entropy of Y is infinite, let us define the entropy of Y this way. The integral of P of Y times the logarithm of 1 divided by P of Y dy cancelling from the beginning the interval size here. So instead of defining the entropy as we always did so far, let us define the entropy this way. Okay. Of course, now the result of this evaluation is not infinite, and we define the entropy of Y given X in a similar way, and so we can say that the information, mutual information, is H of Y minus H of Y given X defined this way. Okay? So the point is, we should put the interval size here and also here. And in this case, we would have infinite minus infinite. Okay? But if we cancel this interval size from the beginning, we have a finite value of the entropy of Y minus a finite value of the entropy of Y given X. Okay? So, this is what we do. Of course, we are completely losing the physical meaning of the entropy, because we know the entropy is infinite. This is not the number of bits we need to encode one sample of Y. Okay? This is something else. But we don't care about the entropy. I told you, we only care about the difference between H of Y and H of Y given X. And the value of this difference we get is right. And this is what we want. You can easily see, since we have completely lost the physical meaning of the entropy, that the entropy defined this way could be even less than 0. We don't worry about it. There is no physical meaning associated to this entropy, to the entropy of a continuous variable defined this way. Okay? Some people say, well, this is not the entropy. This is something else. And so we are abusing notation if we use the same symbol for this entropy, which is not an entropy. We should use a different symbol, and we should use a different denomination. We should not call this entropy, something else, and we should use a different symbol. Okay, people that do not like to say this is the entropy of a continuous random variable, and the entropy is indicated by capital H, say this is something else, for instance, differential entropy. I don't know why differential. Anyway, differential entropy. And differential entropy is different from entropy, okay? So we have entropies for discrete random variables and differential entropies for continuous random variables. And instead of use capital H, we use, for instance, lowercase h. So those people say we have only a differential entropy for continuous random variables, and the differential entropies are indicated by lowercase h. In fact, we know that this is not a capital H, even if I myself keep saying capital H, this would be a capital eta, Greek eta. And so those people should write the differential entropy this way, lowercase eta of y. But many people don't know that this is not an h, and so they use lowercase h. As you probably understand, I don't mind entropy and differential entropy. We know we are using a definition which has a physical meaning for discrete random variables. We are using a different definition which has no physical meaning for continuous random variables. And I will go on saying this is the entropy of a continuous random variable, and I will indicate the entropy with capital H or capital eta, as you prefer. Good. So we see that also when the output is continuous, we have the usual equations for mutual information. That is, we can write, we can evaluate the mutual information this way: h of x minus h of x given y, or h of y defined that way minus h of y given x defined in a similar way, or even, if you prefer, h of x minus h of y plus h of y minus the joint entropy. You can easily see that also this equation works with a definition similar to this one. Of course, when we evaluate h of x, we have a set of probabilities. So we have a summation here. When we evaluate h of x given y, we have a set of discrete probabilities, so a summation also here. When we evaluate h of y, we have a continuous random variable, so we have a probability density of y, and we have an integral here instead of a summation. And we evaluate h of y given x. We have an integral with respect to x, to y, and if we have to take the average also with respect to x, we have a summation. Okay, and here a summation because x is discrete. Here an integral because y is continuous, and here a summation with respect to x and an integral with respect to y. Very simple. So the practical rule is, when the variable, you have a discrete variable, you use the equations we have seen so far. When you have a continuous random variable, you substitute probabilities with probability density and summations with integrals. And that's it. Nothing else. Very simple. What about the properties of entropies, and in particular of mutual information when we have also continuous random variables. We have a list of properties we have learned so far, and let me tell you that almost all these properties do hold also for continuous random variables. Okay. There are 2 or 3 differences that I will mention briefly. First of all, I told you that HOY has no physical meaning, okay? And HOY can even be less than 0, no problem. There is no physical meaning associated with HOY. Let's go back for a while to the discrete case. Suppose we have a variable x, and we have evaluated the entropy of x. Suppose we have another variable y, which is a function of x. And suppose, for simplicity, that g is invertible. So knowing x or knowing y is exactly the same. We know x, we know y. We know y, we know x. Okay, we have seen that in this case, h of y is equal to h of x. In a sense, if we want to encode a sequence of messages, and the messages are taken from the alphabet of x or the alphabet of y, we spend exactly the same number of bits, because encoding x or encoding y is exactly the same. Okay? Suppose, for instance, that x is equal to 0 or 1, and y is equal to 3 or 5, with the same probabilities. The probability of y equal to 3 is equal to the probability of x equal to 0. The probability of y equal to 5 is equal to the probability of x equal to 1. And zeros correspond to 3's and 1's to 5's. Okay? No difference encoding a sequence of zeros and 1's or a sequence of 3's and 5's. Exactly the same. The cost, the number of bits we need is exactly the same. We have exactly the same entropies. Same probabilities, same entropy. What happens in the continuous case? Okay. Since we have lost the physical meaning of h of y, and maybe of h of x if x is continuous, we are not sure that h of y should be equal to h of x. Suppose, for instance, we have a continuous random variable with some entropy. Now, for a while, x is continuous, and we have y equal 3 times x multiplied by 3. Multiplied by some constant. Okay, you put this equation, this change of variable, inside the definition of the entropy, and you will find that the entropy of y is equal to the entropy of x plus the logarithm of 3. This is simply an effect of the change of variable inside the integral. Okay? So, knowing x or knowing y gives exactly the same information. We know x, we know y. We know y, we know x. Yet the entropies are different. No problem. The entropy has no physical meaning. Okay? So we don't worry about the fact that the entropy of y is different from the entropy of x. Okay? So this is one difference between entropies in the discrete case and entropies in the continuous case. But I told you, we don't worry too much about entropies. Suppose we have x is a continuous random variable and y is a continuous random variable, and we have evaluated the mutual information. Now, suppose we have u, which is a function of x, and v, which is another function of y. Okay. And suppose that both functions are invertible. So, knowing x or u is exactly the same, and knowing y and v is exactly the same. Okay, suppose we evaluate the mutual information between u and v. Okay? And suppose that we are not lucky, and the mutual information between u and v is different from the mutual information between x and y. This would be really a problem, because one says, oh, no, this is not impossible, this is not possible. Knowing u is exactly equivalent to knowing x. Knowing v is exactly equivalent to knowing y. So the mutual information between u and v cannot be different from the mutual information from x and y, if our definitions make sense, of course. Okay? Okay, we are lucky. We can prove that even if the entropies change, the mutual information does not change. That is, the effect of the change of variables we see in the entropy of x and in the entropy of y disappears when we take the difference between an entropy and a conditional entropy. Okay? So, we can prove, and this is an exercise left to you, that you know very well, you can manage very well changes of variables inside the integrals, of course. So you should be able to prove that every time the two functions g and h are invertible, we have this equality. So it seems that the mutual information does make sense even when the input is continuous and the output is continuous. Okay? Basically, this is what we had to put into evidence about the behavior of entropies and mutual information in the continuous case. Good. Now, let's consider an important example. Suppose our random variable y has a Gaussian probability density, okay? Which means that the probability density is defined once we know the mean value and the variance. First of all, we don't care the mean value. Suppose we take the random variable y, and we had some constant. So the mean value becomes m plus the constant c. What happens? Simply, this was the probability density, and this is the probability density of the new variable. We have simply shifted the probability density. Okay, let's look at the definition of h of y. The integral of p of y times the logarithm of 1 divided by p of y. And you see immediately that the effect of a shift like this can be cancelled by a change of variable inside the integral. So the entropy does not depend on this shift. It does not change if we shift the probability density. That is, if we modify the mean value of the variable. Okay? So we can assume that this is 0. We can take any value for the mean value of our Gaussian variable, for instance, m equal to 0. Okay? So we have just the variance. Okay? And we expect that the entropy will depend on the variance. Okay, let's try to find the entropy. Here we have the probability density, P of y, equal 1 divided the square root of 2 pi sigma square times the exponential of minus y square divided by 2 sigma square. Okay. We need the logarithm of 1 divided by p of y. Okay. So the logarithm of 1 divided p of y is better to use for a while the natural logarithm, because here we have an exponential. So suppose we wanted to use the logarithm to the basis e, and so we have 1 half times the logarithm to the base e of 2 pi sigma square, and plus y square divided by 2 sigma square. Okay? So h of y is the integral of p of y times 1 half the logarithm to the base e of 2 pi sigma square plus y square divided by 2 sigma square. And here we should consider the basis of the logarithm. So here we have to multiply by the logarithm of e. And now you see that evaluating this integral is very simple, because let's consider this term. This is a constant multiplied by p of y, and the integral of p of y is equal to 1. So this is 1 half times the logarithm to the basis e of 2 pi sigma square. This is the first term. Second term, apart from the denominator here, we have the integral of y square times p of y, and this is the variance. So we have the variance divided by 2 times the variance. And so this is 1/2. And now let's put this 1/2 inside this logarithm. We multiply by e here, and we drop this 1/2. And now let's express the product of the logarithm to the base e times the logarithm of e as the logarithm to the base 2. So finally we have 1/2 times the logarithm of 2 pi e sigma squared. Okay, this is the entropy of our Gaussian random variable. And you see that the entropy depends on the variance, as we expected. And you see, for instance, that if you multiply your random variable by 3, the variance gets 9 times as large, and the entropy increases by 3. No?
Yes.
Multiply this by 9, and you have 1/2 here. That it means that you are getting the same entropy plus 3. The logarithm of, sorry, not plus 3, plus the logarithm of 3. Okay, so this is the variance of a Gaussian random variable. A result we will use quite soon. Another point, suppose that y is not Gaussian and has the same variance. So we are considering a different probability density, but the variable has the same variance. Can we tell anything about the entropy of this new y? Okay. What we can prove easily is that the entropy is less than this value. So given the variance of a random variable, the entropy cannot be greater than this, and this value of the entropy is obtained if and only if our variable is Gaussian. So in general, h of y is less than or equal to 1/2 times the logarithm of 2 pi e sigma squared. With an equality here, if and only if the probability density of our variable is Gaussian. I'm tempted to skip the proof. You can find it in the lecture notes. It takes only a few lines, and so I hope you can follow the proof, and so I can save a few minutes. And there is also a generalization for a vector of random variables. For instance, there is an equation similar to this one for the joint entropy of capital N jointly Gaussian random variables. And of course, instead of the variance here, you will find the covariance matrix. You should expect this. And you can find the equation in the lecture notes, and the task of proving this equation is left to you. Good. Now, we are almost ready to evaluate the capacity of the AWGN channel.
Base E of E. Base E of E.
Why is this?
You need one half. Two and three. This you did nothing. It's one.
Okay.
So now add these two. If you add these two, here E comes inside. Oh.
Oh. Yes.
We are assuming that the noise is independent of the input, as usual. First of all, a general result for channels like this may be with a noise which is not Gaussian in general. That is, channels in which the output is equal to the input plus some independent random variable. Okay. We want to evaluate, we need to evaluate HOY given X, because we wanted to find the mutual information this way, HOY minus HOY given X. Okay. Let's consider the term to be subtracted, H of Y given X, and as we did so many times so far, we will first evaluate the entropy of Y conditional on a specific value of the input. Okay? Well, what happens when we know the input? The output is equal to the noise plus a constant. Okay? But we know that when we add some constant, the entropy does not change. Which means that the entropy of Y given any value of X is simply the entropy of Z. Suppose the input is 0. The output is equal to Z. And so the entropy of the output, given that the input is 0, is the entropy of the noise. Suppose the input is 10, for instance. The output is Z plus 10. But the entropy of Z plus 10 is equal to the entropy of Z. We are simply shifting the probability density. And so, for any value of the input, the entropy of Y, conditional on that input, is equal to the entropy of the noise. Now, we have to take the average with respect to X. And of course, we will find that HOY given X is equal to H of Z. Which means this is equal to HOY minus H of Z. As simple as that. And this is the mutual information. The mutual information is the entropy of the output minus the entropy of the noise. I'm not assuming that the noise is Gaussian. Any kind of noise. Okay? Good. So we wanted to find the maximum with respect to, suppose for instance the input is discrete, with respect to the probability distribution of the input of h of y minus h of z. And this will be the channel capacity. But of course, you see that the entropy of the noise does not depend on the input distribution. And so you see that we have simply to look for the maximum of the output entropy. Find the input distribution that maximizes the output entropy, and then subtract the entropy of the noise. And this is the capacity of the channel. Okay? So, every time we have a channel where the output is equal to the input plus an independent sample of noise, evaluating the channel capacity corresponds to looking for the maximum with respect to the input distribution of the entropy of the output. And once we have found this maximum, we simply subtract the entropy of the noise, and we are done. This is the channel capacity. Okay? Now, let's use this way of calculating the channel capacity, supposing that the noise is Gaussian. Okay? Now, we assume that the noise is Gaussian. So we know the entropy of the noise, because we have learned how we can calculate the entropy of a Gaussian random variable. Okay? Suppose this is the variance is sigma square. Okay, since we have several variances, let's say sigma square z. Okay. Okay, so we have the maximum with respect to the input distribution of h of y minus 1/2 times the logarithm of 2 pi e sigma square z. Here I was supposing that the input was discrete. Suppose the input is continuous instead. The only difference is that instead of having a set of probabilities, we have a probability density of the input. So, use the input distribution, the probabilities if the input is discrete, use the probability density if the input is continuous. This is the only difference. Good. Now, let's look at the output. The output is the sum of the input plus noise. And noise is independent of the input. So we can say, well, the variance of the output is equal to the variance of the input plus the variance of noise. And now, suppose we know the variance of the noise, and suppose we know also the input variance, that is the input power. Of course, you see that if you transmit more power, if you increase the power of the input, the capacity of the channel will increase. Okay? So we have to keep the power, the transmitted power, constant. So we are given a value of the transmitted power, we are given a value of the additive noise, okay? And so we know the variance of the output. And we want to find the maximum entropy of the output. Given the variance, we cannot change the variance because this is the transmitted power plus the noise power. We have seen a few minutes ago that to get the maximum entropy of Y, we should try to have a Gaussian distribution of Y. Given the variance, the entropy is maximum when the distribution is Gaussian. Okay? So, our problem is, can we manage so that Y is Gaussian?
Yeah. X is Gaussian. This happens when X is also Gaussian, because the sum of two Gaussians is...
Yes? Yeah.
Okay.
Ah, this was a...
The answer, yes.
I was supposing it was a question.
No, it was...
It is the answer.
It was trying,
okay.
yes.
Good. Okay, this is Gaussian. We want this to be Gaussian. And there is a difficult theorem. Probably nobody in this room knows the proof of this theorem. I don't as well. The proof is very complicated. There is a property like this. If this is Gaussian and this is to be Gaussian, also X must be Gaussian. Y can be Gaussian if and only if also the input is Gaussian. Okay? And so this is the answer. The optimal distribution of the input is continuous. It is Gaussian. Quite surprising. So we should not transmit a binary input, +1 or -1, a quaternary input, -3, -1, +1, +3, or a multi-level input. We should transmit a continuous input. And the probability density of the input should be Gaussian. Because in this case, the probability density of the output is Gaussian as well. And we are maximizing the entropy of the output. And so we are achieving the capacity of the channel. Good. So, why is Gaussian? So, the entropy is very simple. The entropy is 1/2 times the logarithm of 2 pi e times the variance of Y. But the variance of Y is simply the variance of the input plus the variance of noise. This is h of Y, and now we subtract h of z. 1/2 times the logarithm of 2 pi e sigma squared z. And you see some cancellation, and the result is 1/2 times the logarithm of, let me write it as we usually do, 1 plus sigma squared x divided by sigma squared z. We have the sum of the variances here and the variance of noise here. And this is a very simple equation for the capacity of the additive white Gaussian noise channel. Basically, the capacity depends on the ratio of the transmitted power and the noise power. So this is what people call signal-to-noise ratio. This is the ratio of the useful power, the transmitted power, and the noise power. This is, in many cases, you will find that it is written this way: 1/2 times the logarithm of 1 plus SNR, signal-to-noise ratio. And quite oddly, the capacity of this channel is achieved with a continuous input, not a discrete input. Okay? And this fact is known from the very beginning of information theory. You can find this equation in the first paper by Shannon, 1948. Okay? So, at the very beginning, people knew that in order to achieve the maximum capacity of this channel, one should transmit a continuous input instead of a binary input or a quaternary input or a multi-level input and so on. Okay? Well, what do engineers do? When engineers were informed that the optimal input distribution is Gaussian, they told Shannon, "You are joking. We will never transmit a continuous input. We, at that time, we transmit +1 and -1 and nothing else. So you are really joking. We will never follow your indications." Okay. Well, let's ask ourselves what happens if we do not obey this rule and we say, okay, x is equal to +1 or -1. I don't want to transmit anything else. Okay, good. So you put a constraint, x is equal to +1 or -1. I don't want to transmit anything else. I want to transmit, in a sense, 1 bit. Okay? Don't tell me I should do something else. Okay, so the input is binary. We are putting this constraint, so the input power is 1 in this case, but we can change the signal-to-noise ratio, changing the variance of the noise, of course. And so, let's find the capacity of this channel with this constraint, which is wrong, we know, but for simplicity we wanted to transmit only 2 levels. Okay, we have to evaluate h of y and nothing else, because h of z is known. Okay, so the problem is evaluate h of y. And once we have found h of y, we know the mutual information. That is, we know the capacity of this constrained channel, of the channel which is constrained to transmit a binary input. H of y. Well, we need P of y. Once we know P of y, we are done. We evaluate the integral, and this is the entropy. This is y, this is P of y, And everybody knows that we can condition on the two values of the input. Probably you can guess that we should use +1 and -1 with equal probabilities. Anyway, we can try even different probabilities. Okay, when the input is 1, the output is z plus 1. When the input is -1, the output is z minus 1. That's it. And so, this is the probability density of the output when the input is 1. This must be multiplied by the probability of transmitting 1. And this is the probability density when the input is -1. Here I'm assuming that we transmit +1 and -1 with equal probabilities. Suppose you wanted to use different probabilities, you raise this function and you decrease this one. Okay, something like this. Okay, these would be different probabilities. Okay. Now, P of y is the sum of these two terms. So P of y is something like this. Okay? This is P of y. And now you put this probability density inside the definition of the entropy and you evaluate the entropy. That's it. Okay? Some hope to do the evaluation analytically? No, of course. So you have to find this entropy numerically. No problem. You put the probability density inside a numerical quadrature rule and you find the entropy. Okay? You can modify the variance of the noise. This corresponds to one value of the noise. You can increase the variance and you can decrease the variance, of course. So you can evaluate the entropy of y for several values of the variance of the noise, and then you subtract the entropy of the noise and you find the mutual information. Okay? What do you get if you make this evaluation? You can see the results in a figure in the lecture notes, figure 4.1. Here you put the signal to noise ratio. Well, actually this is 1. Okay, let's say in the binary case this is 1 and this is the variance of the noise. Okay. And here you plot. Let me say it is the channel capacity. It is not the channel capacity. It is the constraint channel capacity. Once we have put the constraint that the input must be binary, this is what we can get. That is, this is the constraint channel capacity. And well, if you look at this graph, you will see that this axis goes from -10 to 30. What is a negative signal to noise ratio? Of course, we are using the old habit of engineers of giving the signal to noise ratio in decibels. Some about 100 years ago, somebody told, oh, we could measure signal-to-noise ratios taking the logarithm. And so somebody introduced this strange unit, decibel. And we are still going on using decibel. I don't like them. Sooner or later, somebody should tell, okay, we are fed up with decibels. Please don't use decibels anymore. But so far, people keep using, have kept using decibels. Okay, so this is the signal-to-noise ratio in decibels, and this is the channel capacity. Of course, when you have a better signal-to-noise ratio, you have more capacity. And so the capacity is 0 when the signal-to-noise ratio is extremely low, and then increases this way, more or less. Don't try to copy my figure here. You have the right version of the figure in the lecture notes. And then you get an asymptotic value, which is, of course, 1. Don't forget that we could evaluate the channel capacity this way: h of x minus h of x given y. And this is 1 if we transmit the two levels with equal probabilities. Okay? So the capacity cannot be greater than 1. The mutual information cannot be greater than the information at the input. Okay? So suppose there is no noise at all. What you receive is the input. That is, you receive 1 bit of information. Even if the signal-to-noise ratio is extremely large. So you have a saturation here. The mutual information cannot be greater than 1. Okay? You can increase the signal-to-noise ratio as much as you want. You do not increase the capacity further. Good. Now, suppose one says, well, instead of transmitting 2 levels, I try transmitting 4 levels. Suppose one say, okay, x can be equal to -3, -1, 1, or 3. We are using a multi-level transmission system. Okay? Now, you can repeat the same evaluation. Here you have 4 terms instead of 2. You have to take care of the probabilities of the levels. Suppose, for simplicity, that you transmit these 4 levels with equal probabilities. 1/4, 1/4, 1/4, and 1/4. So this figure gets something like this. Okay? And the probability density of the output is like this. Okay, you put this probability density inside the equation that evaluates the entropy of Y. You subtract the entropy of the noise. You make this calculation for many values of the entropies of the variance of the noise, and you plot your results. Okay, what happens? You can find what happens in the lecture notes, but more or less you obtain the same results here. And then something like this. Of course, now the maximum information you can transmit is 2 bits because you have 4 levels. And so if there is no noise, you are transmitting 2 bits of information. Okay? So the saturation level is 2 bits per channel used. Every time you use this channel, you can transmit at most 2 bits of information, provided the signal to noise ratio is very high. Okay? So what do we learn from these 2 curves? If the signal to noise ratio is small, the noise power is high with respect to the power we can transmit, there is no difference between transmitting 2 levels or 4 levels. Transmitting 4 levels is completely useless if the signal to noise ratio is small. But if the signal to noise ratio is large enough, we can gain a lot transmitting 4 levels instead of 2. And in particular, you see, suppose your goal is to transmit just 1 bit per channel use. Okay? You want to transmit 1 bit of information every time you use your channel. If you use a binary input, you need an infinite SNR. If you use a quaternary input, this is the SNR you need. So if you want to transmit 1 bit of information, you should not use 2 levels. You should use 4 levels. An old engineer says, oh, this is quite odd. I want to transmit 1 bit is 2 levels. What are you telling me? No. You want to transmit 1 bit, you cannot use 2 levels. If you transmit 2 levels, you need a huge SNR. You have to transmit 4 levels. I don't consider 3 levels for simplicity. 2 levels or 4 levels, of course. Okay? Well, suppose you want to transmit an information which is close to 2 bits per channel use. You discover soon that you cannot transmit 4 levels because you have a saturation also here. This is 4 levels, this is 2 levels. You can transmit 8 levels. And if you repeat your evaluation with 8 levels, from -7 to +7, you will find at the end of the evaluation that you get something like this. So do you want to transmit 2 bits of information or something like 2 bits of information? Don't even think of using 4 levels. No, this is completely wrong. You have to use at least 4 levels, 8 levels. Okay? And we can plot here also the magic equation 1/2 times the logarithm of 1 plus SNR. which is the capacity we would achieve transmitting a continuous random variable. And if you plot this here, you will find something like this. More or less the same result in this part, and then something like this. That is, if the SNR is very small, transmitting 2 levels or 4 levels or an infinite number of levels, a continuous random variable, gives the same capacity. But if you have a large SNR, transmitting a Gaussian random variable is better than transmitting 2 levels, 4 levels, 8 levels, and so on. Another point, if you look at this figure 4.1 and you look at the derivation, you will find that this set of figures, of graphs, has been obtained assuming that the levels, 4 levels in this case, are transmitted with the same probability. 1/4, 1/4, 1/4, 1/4. 8 levels, 1/8, 1/8, 1/8, and so on. Okay? One could say, okay, let's try a different probability distribution. We transmit +1 and -1, the inner levels, with some probability, and the outer levels, +3 and -3, with a different probability. Why not? Let's try. So we have an additional degree of freedom. Of course, if we are using 2 levels, we transmit them with the same probability. But if we have 4 levels, we could say, okay, we can increase this probability and decrease this one. Okay, suppose you work out this optimization problem, which is given the input power and given the power of the noise, find the optimal input distribution that maximizes the entropy of the output, as usual. Okay? And you will find that you should use different probabilities. You should not use equal probabilities for the levels. And you will also find, don't try to do this by hand, ask the help of MATLAB or something like that. You will find that the optimal input distribution depends on the signal to noise ratio. So there is not an optimal, just one optimal input distribution. There is one optimal input distribution for each signal to noise ratio. Okay? And you will find, here again we have the SNR in dB. You will find something like what is shown in figure 2, which is a little better than figure 1. Okay. And if you plot also this equation, here you find something like this. And the real point is, if you use different input probabilities, usually we say if we shape the probability distribution, we don't use equal probabilities, but we use smaller probabilities for the outer levels and higher probabilities for the inner levels, chosen with probabilities chosen in an optimal way. The performance we get is very close to the performance we could get with an infinite number of levels. And basically, look at the Gaussian receipt. We should use an input probability density like this, for instance. Okay. This is given the variance of given the input power. This is the probability density, the optimal probability density of the input. Okay. An infinite number of levels. Well, basically, when we use only 4 levels, what we do is taking these probabilities. Higher probabilities for the inner levels and lower probability for the outer levels. In a sense, we are trying to approximate a Gaussian probability density with a finite number of levels. And so information theory tells us that if we have a sufficiently high signal-to-noise ratio and we want to transmit as much information as possible, we can use a multi-level input with a sufficiently large number of levels, and we have to shape the probabilities of the levels in a way which is very similar to the Gaussian probability density. Okay?
Mm-hmm.
So we have to choose a transmission system where the 4 levels are transmitted with different probabilities. When engineers were informed that they should do that, they told Shannon and his followers, you are really mad. I will never transmit 4 levels with different probabilities. And the answer of information theory was, you will be punished. You don't want to do your best, you will transmit less information than possible. Okay? More or less in the 90s, more or less around the 90s, engineers tried to transmit multi-level information using non-equal probabilities. And they found that it works. The performance of the system is improved if you are able to transmit information this way, using different probabilities. Engineers did that in radio systems, typically, and also in systems like ADSL or something like this. Eventually, also optical people got convinced that this method of transmitting information should be tried. And in the very last few years, also optical transmission systems are trying to use different probabilities of the input levels. And it works. You can gain. How much do you gain? How much difference between the performance of different probabilities and the performance of equal probabilities? You can compare figure 1 against figure 2, and you will see that at very high signal-to-noise ratio, you can gain the equivalent of, there is a theory behind that, you can get up to 1.53 dBs at highest NR. Okay? Is this 1.5 dB very much, or a little gain? Well, I learned from people working on optical transmission systems. We collaborated with them for several years, that they mind 1/10 of a dB, and in many cases half of that. They say, okay, we can get 0.05 dB, that's good. So you see that 1 dB and a half is a huge gain. Okay? So eventually they got convinced that they should try transmitting with multi-level, with many levels, using different probabilities. And I can tell you that it works, even in optical transmission systems. Okay? And this was known 60 years ago, or 70 years ago. Okay? But people told, no, we will never do that. And they now are doing that. I have some material from your homeworks. Some people